Good evening, our dear viewers. Welcome again to our YouTube channel and the chemistry series lessons. In this particular video, we are going to talk about chemical equilibria, and in common or in main focus is going to be about the factors that affect equilibrium constant and the position of the equilibrium. Going forward, we are going to be talking about that this topic is the one which deals with chemical reactions in which the concentration of reactants and products are not changing with time. We have both the forward and backward direction, so we are going to be talking about reversible reactions. One stage, the reactants combine to form the products, and in another stage, the products also combine to form the reactants. And when both the forward and backward reaction are equal, then we shall say that an equilibrium has taken place. For example, if we look at a reaction of A reacting with B to form C and D, we have both the forward and backward reaction. When such a reaction undergoes equal combination or equal rates both forward and backward, we shall say that the reaction has attained equilibrium. Equilibrium, when we consider these reactions, we are going to have the rate of reaction being equal to the rate of reaction is defined as the decrease in the concentration of reactants per unit time and the concentration of products per unit, or we can say that this is when the increase of concentration of products is there, so that is the rate of reaction. So when we have rate of reaction reacting with backward rate of reaction and forward rate of reaction being equal, then we shall say that we have attained our equilibrium. For example, when we see in this equation here, we have iron reacting with steam. Going forward, iron can react with steam to form triion tetraoxide, while also triion tetraoxide can still react with the hydrogen gas to form back iron and steam. So such a reaction is one of the examples of reversible reactions. When we go on, we can say that these equations are dynamic. That means we don't reach a state of statics, or it is not a static reaction, because there is always a constant reaction between forward and backward. So it is a dynamic reaction. At any time, both reactants and products are reacting to form the other reactants, are reacting to form products, and some products are reacting to form back the reactants. Now we can talk about the Lechatellier's principle, that if now we are looking at the above system, for example, and it has attained equilibrium, and if we disturb it, then that means the system will react to relieve the stress of the change. So there will be a shift in equilibrium which will either favor the forward or the backward reaction. So that is what we call, or what is known as, the Lechatellier's principle. So depending on this Lechatellier's principle, we are going to be able to look at some factors which affect the position of the equilibrium and the rate of equilibrium. However, before we can go forward, let us look at the equilibrium law, or what we can know as the law of mass action. So this tells us that if a reaction has allowed it to reach equilibrium, then the product of the concentration of the products is equal, divided, let me come again. The ratio of the concentration, the product of the concentration of the products raised to the appropriate powers divided by the product of the concentration of the reactants also raised to appropriate powers is a constant. So this constant ratio is known as the equilibrium constant, which can either be Kc or Kp. Kc is the one which is in dealing with terms of molar concentrations, and Kp is the equation or equilibrium constant for a reversible reaction when these have been expressed in terms of partial pressures. For example, if we have a reaction A and B reacting both forward and backward to produce C and D, and we say that this equation has reached equilibrium, we can have the following expressions standing for the Kc. So square brackets in chemistry mean concentration. So we have C and D as our products, and A and B are our reactants. Also, in terms of partial pressures, we can have the Kp expression given as above, whereby C, D, A, and B, which is in small letters, are the stoichiometric coefficients used in balancing the equations at the equilibrium state. We can also note that Kp is for only those reactions which involve gases. That means both the reactants and the products are in gaseous state. However, Kc can be used for both gaseous state and those in liquid or aqueous state. However, we can also note that during this, the concentration of the solid is taken to be as unity. For example, if we have iron, which is a solid, then its concentration will be 1. Triion tetraoxide, which is also a solid, when dealing with the above expressions, can also be taken as 1, which same applies to their partial pressures. Now, when we go to the factors which affect our equilibrium, we have the first change in the effect of change in concentration. For example, you're going to be looking at an equation which is having, or for the equation for the Haber process, that is nitrogen reacting with hydrogen to form ammonia. We can write the expression for Kc as shown and the expression for Kp as shown. Then concentration does not affect the equilibrium constant. That is, if the reactants increases, then also they react more to form the products. That means the increase in concentration of the reactants drives the reaction forward in order to increase the concentration of the products. Therefore, the position of the equilibrium shifts to the right. Similarly, when we increase the concentration of the products will now react in the in the backward direction to produce more reactants. That means our equilibrium will shift to the left, and however the value of Kc remains constant. That means, therefore, that the change in concentration only affects the position but does not affect the value of the equilibrium constant. So if a substance is added, the reaction tends to move in the direction which will consume the substance added, and if a substance is removed, then the reaction tends to move in the direction that will replace the product which has been removed. We go ahead to change in pressure. However, this change in pressure, we're going to look at it in two types. Type 1 is one which involves reactions whereby number of volumes or number of moles in the reactant side is more than the number of moles in the product side. For example, in the Haber process, we have a total of 4 volumes on the left hand side or on the reactant side, and only 2 volumes on the product side. So if the pressure is increased, the equilibrium shifts to the right. This is because the forward reaction is the one which is leading to a reduction in volume. When we increase pressure increases and the volume decreases. Therefore, we are going to be favoring the forward direction because it is one which is proceeding by decrease in volume. So that means we shall be favoring formation of more ammonia. When we go forward, we have type 2 of molecules. These volumes, this is whereby we are having equal number of moles both on the reactants and on the products. For example, hydrogen reacting with iodine to form hydrogen iodide. When we increase pressure, there will be no change because we don't have any significant change. Similar, when decrease pressure, we have no significant direction to take because we have equal number of moles and equal number of moles both on the reactant and the product. That means for type 2, we do not have any shift in equilibrium or the position of equilibrium. Therefore, pressure for this case does not affect anything. We can go forward and look at type 3 of the reactions. In this case, these are the ones we are going to look at. The number of moles on the reactant side being less than the number of moles on the product side. For example, the thermal decomposition of phosphorus pentachloride giving us phosphorus trichloride and chlorine. When we increase the pressure, there will be an increase in the number of moles of phosphorus pentachloride because the backward reaction is one which leads with decrease in volume, hence increase in pressure. Therefore, in order to keep Kp constant, phosphorus trichloride and chlorine will decrease and increase the concentration of phosphorus pentachloride. That means the equilibrium will shift to the left, therefore backward reaction, and hence when reactions increase in pressure, shifts to the equilibrium, and the decrease in pressure shift the equilibrium to the right. So we go ahead to change in the volume of the reactions involving gases. This one here, we can also look at the example of Haber process, but in general, changing volumes in reactions involving gases, volume does not effectively affect the position of the equilibrium. However, when you increase volume, the pressure decreases, and if the pressure decreases, then we are going to be dealing in the side which leads to decrease in pressure. For example, in this case, if we are dealing with the decrease in volume, the pressure will increase, and this causes the reaction to move to the right, because this will tend to oppose the changes in decreasing the volume present. When we look at example of nitrogen reacting with oxygen to form nitrogen monoxide, here there is have no change, volume will have no change, and generally for decrease in volume or increase in pressure, the reaction tends to move in the direction which reduces the number of moles of the gas. Then for an increase in volume or decrease in pressure, the reaction tends to move in the direction that will increase the number of volume of a gas. We move ahead to the effect of catalysts on the equilibrium constant and equilibrium position. However, we all know that a catalyst is only a substance which increases the rate of a chemical reaction. That means also in our case, it will only increase the rate at which equilibrium is attained. So therefore, it only affects the time it takes a reversible reaction to reach equilibrium. Finally, it means that a catalyst will only change the rate of both the forward and backward reaction in the same degree. So also a catalyst only does not change the position of the equilibrium and does not change the value of the equilibrium constant. We go forward and we look at the effect of temperature. Temperature affects both the position of the equilibrium and the equilibrium constant. An increase in temperature also leads to absorption of heat. That means if a reaction is endothermic, then increase in temperature favors that reaction. For example, if we look at the Haber process, we have the Haber process, and the heat change in this case is negative 92 kilojoules per mole. So if we need this reaction to go forward, since the reaction is releasing heat, then that means we need low temperatures. When we increase the temperatures, then we shall be favoring the backward reaction. That means for a Haber process and contact process of that case, whereby the reactions are exothermic, these are favored by decrease in temperature. So for the Haber process, in this case, if it is to be operated, we have to operate it at around 450 degrees Celsius to 500 degrees Celsius, so that we can have a reasonable amount of ammonia which is going to be formed. If we increase the temperature, then we shall be decreasing the amount of ammonia collected. Next, we look at the addition of an inert gas in the equilibrium mixture at a constant pressure. So when we add an inert gas is something which does not react with any of the contents in the equilibrium mixture or does not affect anything. It is inert. For example, helium gas, which is inert gas, but in this case, considering addition of that inert gas at constant pressure. So when we look at Haber process, both nitrogen, hydrogen, and ammonia in gaseous state, before we add helium, the total pressure is dependent on the partial pressure of nitrogen, hydrogen, and ammonia. But when we add helium, the total pressure is to be kept constant. That means the total pressure now includes the partial pressure of helium. So in this case, there is no change in the pressure of the system, but there is a change in the pressure of the initial gases which were at equilibrium. That means nitrogen, hydrogen, and ammonia have to adjust themselves in a direction so that their pressures decrease, and the only direction in which we favor the direction of the pressures of these gases to decrease is the backward direction. That means our equilibrium is going to be shifting to the left, so that we can accommodate the extra pressure which is being brought about by the helium gas. So therefore we shall have an equilibrium shift from the left, from the right to the left. However, the position and the value of the equilibrium constant remains constant. Then lastly, we shall look at the effect of adding an inert gas to the equilibrium mixture at constant volume. And we shall say at constant volume, addition of an inert gas increases the total pressure, but partial pressures of the initial components of the reaction remains constant. Therefore, the Kc and Kp remains constant, and the position of the equilibrium is not affected. So at constant volume, addition of inert gas, there is no change in the position and the direction of the equilibrium. So dear listeners, please, you can go ahead and try out this question and explain what takes place when argon is added to the mixture at constant pressure and when argon is added to the mixture at constant volume. Thank you, and that is all for today. Please, this is about the factors affecting chemical equilibrium and how they affect the equilibrium position and the value of the equilibrium constant. Feel free to ask some questions in the comment section, and if you need any video which should be worked up on you, please put it in the comment section and we shall be pleased to deliver that in our next video. Thank you. This is Hope Chemist. I remind you to always subscribe.